I have posted the first homework assignment on our class webpage. Remember, you can get to it by following the link from the syllabus. You know, this thing here that I handed out on the first day. I hope you have that. So check it out. There's also a link from Blackboard to get to that page. But the assignment is just problems from the textbook. I just heard that some people can't see the textbook yet. So maybe I will also, just this time around, I can make a PDF out of those book pages and send it to everybody so that you can see the problems. I believe it is illegal for me to do that, so I'm not going to do that, all semester long. But this time, certainly we can do that. Anybody got questions about the homeworks? So it's going to be due on Wednesday, and the homework due on Wednesday is always what we did the previous week through Friday. So it covers. It does include stuff that we're going to do today, but that's it. All right, great. Sorry about the book thing. I've been in touch with the guy, the publisher, who assures me that everything is working now, but I guess that's not true. So I will work on it some more. This is the first time we've used this. This sort of system is all new at the university this year, so I guess they haven't figured it out yet. Okay. Thank you for your patience. Let's talk about our first sort of non-review topic, although maybe many of you have seen this before, but I'm going to pretend like nobody has seen this before. The area between curves is the first thing I want to talk about. The area between curves. So the ordinary integral is for measuring the area under the curve. That is to say, the area between the curve and the x-axis. But here I'm talking about other sorts of areas. Maybe like here's a function f of x, and here's another function g of x. And you could ask me, or I could ask you, sort of, what is this area between those two curves? That's what I'm talking about here. This I will refer to as the area between curves, right? This is measured in the same basic sort of traditional way that we think about the area as measuring, or the integral as measuring area. If I did have, say, two curvy things like this, and I wanted to know about what's this area here, the way that you would set this up, at least from a theoretical point of view, would be just like with the ordinary integral. You would imagine taking this area and sort of dividing it up into a bunch of little rectangles and then adding up all the rectangle areas, which you could approximate by doing some kind of like a Riemann sum, which hopefully you've heard of, but we're not actually going to go through the details of that because everybody knows that's a real pain to do. The only reason I bring this up is that we are, in this course, going to talk at different times about many different types of, you can use the integral to measure this kind of a thing or this kind of a thing. And it always involves thinking about the thing as being broken down into a bunch of tiny little bits and somehow adding all the bits together. That's what the integral is really all about. But anyway, these little bits here, of course, we imagine that their widths are all like some kind of little delta x quantity, which eventually you take a limit as delta x goes to 0. What about the heights? The heights here, if this is f of x and this is g of x, here each rectangle height Can anybody say what it is in terms of this business here? Yeah?
F of x minus g.
Yeah, it would be f of x minus g of x. That's because f of x is the function up top, g of x is the function down here, and if you want that sort of vertical distance there, f of x minus g of x. It's always the bigger minus the smaller, right? This is always, in this example, f of x is on the top, but it's always the bigger, would you mind? Biggie minus smalls, if you will, right? It's the bigger function minus the smaller function is always how you set that up. Now, the area, if you were thinking of it in terms of rectangles, as rectangles, the area would be, like if you wrote this out as a Riemann sum, which, like I said, we're not going to go through the details of this, but it would be something like the sum of a bunch of things where you do the height of each one times delta x, and those heights would look like f of x, minus g of x. I wrote f of x sub I minus g of xi. If you ever went through the actual details of setting up the Riemann sum, this is what it looks like. You multiply a bunch of different heights of things each time times the delta x, and then you do some kind of limit as delta x goes to 0. If you actually want to do the details of this, it's quite complicated. But since you already know how these things go, this Riemann sum is just equal to the integral of that function right there. And so the upshot to all of this is that sort of this shaded area here, this area equals the integral of f of x minus g of x dx. I guess I don't really want that parentheses there. All right, where the integral, of course, this is a definite integral. If you had the value on the left, we always call, what's happening? This is, I will call a to b, right? If I'm looking at the range of x values from a to b, then this would be the integral from a to b. All right. That was a lot of explanation, all leading up to this basic setup. So if you want the area between two curves, all it is the integral from one end to the other end of the bigger function minus the smaller function. And that's all there is to it. All right. This is sort of in simple examples, this is simple. There are examples where it gets more complicated, but this is the basic idea. So let's try a simple example first. And maybe I'll just say near this box, this is always the bigger one, and this is always the smaller one, right? If you get it backwards, then basically your answer will be negative of what it's supposed to be. All right, let's try, this is an easy example. How about the area between x and x squared? How about that? All right. Ordinarily, you might see some other from here to here, like from a to b or something. But actually, these are two functions which, if you think about the graph of them, these are simple enough functions. I hope everybody knows what the graph of x and x squared looks like. X is just this line, right? And x squared is a parabola that goes up like this. So it's like that. So the area I'm referring to is that little chunk, which is actually in between them. This business. That's what I'm talking about. This little area here. Not too big, I guess. All right. So we can set this up as an integral. What would it be? It would be something like the integral of something minus something dx. It's always the bigger minus the smaller. And looking at the picture, can anybody say what's the bigger function in this case? Yeah? Yeah, x is the bigger function. That's a little weird. Like ordinarily I think of x squared as being bigger than x, but in this little part that I'm talking about, this part of the picture, the x is above the x squared. The line here is up top. So the integral will be x minus x squared. This is an easy integral to do. Doing a problem like this, though, does require that you know what the picture looks like, right? In this example, it's easy enough. So if I'm going to ask you to do this, say on one of our quizzes or tests or something, remember you're not going to use your calculators on quizzes. So I think it would be reasonable to expect you to just know what this picture looks like. For more complicated functions, like on the homework, there are some very complicated ones where I would expect you to just graph it on a calculator and look at the picture so that you'll know what it's supposed to look like. But simple ones, I might expect you to be able to tell. All right, anyway, one last thing is we need to know these guys from where to where. And actually, that's another ingredient that I haven't really told you about, but we can figure it out. It would be, those two numbers would be sort of this x value and this x value. That's like the a and the b that you use in the integral. From here over to here. Now, it's pretty clear on my picture, a is 0, right? Because because it is. That's where the line meets the parabola. There's another point where the line meets the parabola. Can anybody say where that other one is? Maybe show me the fingers. You've got the fingers. They are doing this. It is x equals 1. Yes. Thank you for choosing that finger and not the bad one. Yeah, B is 1. How would we figure that out? I mean, in this example, it's not so hard to just sort of, by common sense, you know that that intersection point is x equals 1. But how would we figure that out if it was more complicated? Yeah?
You set them equal to each other?
Right. If you want to find these two intersection points, you set the equations equal to each other and then solve for x. So, I mean, this one is easy enough to just sort of do in your head, but just for the sake of future generations doing harder versions of this problem, to find the intersection points, let me just write it out, although it's easy in this example. You go x equals x squared, so you set them equal. And then you solve this for x. To solve this for x, I would, you could take a square root on both sides, but you want, no, you cannot take a square root. I was going to say you can divide by x on both sides, but you want to make sure you don't lose any of the solutions, so I'm going to do it like so. Subtract it all onto one side and then factor like so. And now I can say x equals 0, x equals 1, right? Sorry, I'm off the bottom. So anyway, those are the two values. These are the x values of the intersection points. All right. So what's the actual area? Well, you just do this integral. This is all the setup. In these problems, the setup is often harder than doing the integral, because in this case, it's not hard to do. Yeah?
How do you how do you know which one to pick out of the points, x or y, from the intersections? You know what I mean? Like, how do you know it's 1 and not whatever 3?
Yeah. You should be choosing the x values because this is an integral where the variable is x. So the idea here is I'm measuring the vertical heights of this region all the way from the left side across to the right side.
Okay.
And the left.
Because the x is a variable, you just pull x.
Yeah, right.
Okay.
Yeah. Yeah, we only want x. All right, let's just actually do the integral. It's an easy integral to do in this example, just for the sake of getting the actual answer. So I go 0 to 1 x minus x squared dx. And we do the integral. It's 1/2 x squared minus 1/3 x cubed. That's the antiderivative. And I plug in 0 and 1. And it's going to be, I plug in 1. That's 1/2 minus 1/3. That's when I plug in 1. And then I subtract. And I plug in 0. It's going to be 0 and 0. So the answer is 1/2 minus 1/3. Which I think is 1/6, but I don't really care about that. But anyway, that's the answer. That is the area between those two curves. Any questions about that? Any thoughts? Excellent. Okay, that I would consider to be an easy one. And there can be harder ones for a lot of reasons that could make it harder. I'm going to talk in particular about sort of two different ways that these can be harder ones. So one way that it can be harder, this is a harder one, that's what I wrote, harder, would be, I would say, extra intersection points. And here's what I mean by that. Let's say, let's say I have one function like this. This is y equals 2x plus 1. And then I have another function, y equals negative x. And I want this shaded region here. This is 2. All right. So you might, if this were a homework problem or something, I might just show you the picture and say find the shaded area, or I might say this in words. I could say something like the area between y equals 2x plus 1 and y equals negative x from x equals minus 3 to x equal minus 2, plus 2. Right? What makes this harder is what I said. There is an extra intersection point in the middle, right? and I didn't tell you where this point is, but there's an extra intersection point in the middle, which means when you set up the integral, the integral is always supposed to be the bigger one minus the smaller one. But here it's kind of like, well, on this part, this is the bigger one, but on this part, this is the bigger one, right? At that intersection point, the bigger and the smaller switch. And so in this case, we have to set this up as two separate integrals. It's sort of the piece on the left, this piece, which uses this line as the bigger and this line as the smaller. And then there's also this piece, which is the other way around. This is the bigger and this is the smaller. And you have to just do it as two things separately. So we're going to do something like, well, actually, I think before trying to set it up in two pieces, we should find where that extra intersection in the middle is. The x value of that extra intersection point. We do this by setting the equations equal to one another. This one, I don't know if I can say just off the top of my head what that is, but I'm going to find the intersection in the middle. By setting the two formulas equal to each other, that would be 2x plus 1 equals, come on now, negative x. And then this is not so hard to solve. You add the x over there, 3x equals minus 1, right? X equals negative a third. So this is that extra point in the middle where the intersection is. And now I'm going to set this up as two separate parts, the piece on the left and the piece on the right, and then you add the two answers together. So it will be, the piece on the left would be the integral from minus 3 up to negative a third. Sorry, I had to scroll the picture away. Maybe I'll just copy it down here. The piece on the left goes from minus 3 up to this point, which apparently is x equals negative a third, right? And then here I go big function minus the small one. In this case, I didn't pull down enough of the picture. In this case, the big function is minus x, and then I subtract the small function, which is 2x plus 1, right? This is 2x plus 1. This is minus x. So for the piece on the left, that's this piece. All right? And then the piece on the right is the other way round. The piece on the right, this one, is the integral from minus a third up to 2. And now the big and the small are the other way around. So 2x plus 1 minus negative x, like so. All right? And I'm going to do each of those separately and then add the answers together. Everybody feeling good about this so far? What's a little tricky about this is if I just asked you, like if this is all you saw in the question, you might be tempted to immediately set this up as integral minus 3 to 2 of something minus something. But that's actually not what it is. It's because there's sort of like a secret intersection point that I didn't even tell you about. And it becomes your job to make sure, either make sure there is no intersection point, in which case it really is just this, or you have to find the intersection point and then break it up into two pieces, as we did here. All right. By the way, I hope you wrote these parentheses in here. They do make a difference. I know there's some. I don't know if you've ever encountered parentheses haters. There's some people who just don't like the parentheses. I don't know. I don't sympathize. But anyway, let's. Can we just do each of these integrals and see what we get? This first one, they are not hard integrals to do, right? It's minus 3 minus 1/3. If I resolve the parentheses, it looks like negative x minus 2x gives me minus 3x minus 1 dx, right? And then that, I can do the integral easily. It's negative 3 over 2x squared minus 1 becomes x when you do the antiderivative. Plugging in negative 3 and negative 1/3. Sorry, I'm kind of out of room here. This gives me minus 3/2 times negative 1/3 squared minus negative 1/3 minus the whole other thing plugging in negative 3. Minus 3/2 times negative 3 squared minus negative 3. I squeezed it in. I'm zoomed. All right. So that's the area of the first piece. If you like, you could plug all that into your calculator or something, but I don't really care about that. And then the area of the second piece, we do the same kind of a thing. So this is going to be minus a third to minus 2. Just simplifying to begin with, 2x plus 1 minus negative x, that's a plus x, which makes it 3x plus 1 dx. And then I do the integral. This becomes 3/2 x squared plus x, plugging in minus a third and minus 2, which is 3/2 minus 2 squared plus minus 2 minus 3/2 negative a third squared plus negative a third. All right? That's the other part.
Is
Yes?
it positive 2 or negative 2?
Oh, it's positive 2. Yeah, sorry about that. This guy here was a 2. I made it negative. Yeah, this doesn't make a lot of sense. Sorry about that. So this is negative, positive here, positive, like so. Now I have some redundant parentheses. That's fine. All right, so what's my final answer? It's this thing plus this thing is my final answer. So the final area, and I don't really care if you rewrite all of that stuff. My final area is, can I just say like this thing in a little box plus this thing. And if you're doing a problem like this on the homework or a test or something, it's totally fine with me if you want to write it like that. It's a real pain to rewrite everything. You might mess it up. All right. I hope that makes sense to everybody. Finding the extra intersection there is a bit of a pain, but it's more or less the same function to do the integral of both times. It's just the signs are backwards. Right? Excellent. I got one other way that these can be harder, and then I have some for you all to try. And we have plenty of time today for you all to try it. One other way that these can be harder. So that was harder because of extra intersections. Another way that it can be harder is what I'll call sideways. This is not actually a lot harder. It's just you have to sort of know what to do. What about something like the area between y equals 1/2 x and here's the weird part, x equals y squared minus 3. X equals y squared minus 3 is a weird formula, right? That's not it's not a traditional function of y in terms of x. It's a x in terms of y. But anyway, we can still, first of all, draw the picture just to get a feel for what I'm even talking about here. Y equals 1/2 x, that's no problem. That would be a line like this, right? A line with slope half. And then the other one, x equals y squared minus 3. This is some kind of a sideways parabola, all right? If you were looking at, let me just, I'll erase this in a moment, but just a little sidebar. X equals y squared, anybody know what that looks like? It looks like a parabola. It looks like a sideways parabola. Which way does it go? It's over here. Whatever you do, I see backwards. I can't tell if you're right or not. To me, it goes this way. Is that backwards? That's like this, right? Because those are the x values and the positive y values. You know, that would look. Oops. So this x equal y squared would look like this, going through the origin, of course. I just missed the dot. And then what about this? This is a variation on that. That says basically you do this, but then you subtract 3 every time, and you are subtracting 3 from the x values. So this will be moved to the left by 3. It's this picture, but moved to the left by 3. That's what this looks like. So it's something like this. It looks terrible. It should be centered around the, not much better, but a little better. That's what the picture looks like. All right. Do it sideways, I said. You have to draw the picture sideways in this case. So generally speaking, you might see a function where it's y in terms of x, or you might see a function where it's x in terms of y, and you might even see sort of a mixture of the two styles, right? Here I have one sort of traditional function, y in terms of x. Here's the other way around. Now that we know what the picture is, you should just be able to set up everything in the same way. Actually, that's not quite true. This is kind of a problem. If you think about this area, okay, so it looks like this. It has that kind of a shape to it, right? But our traditional method is based on this kind of way of thinking about the area. And this is super weird because this rectangle, its height would be given by this function minus this function. No problem. This rectangle, though, its height is given by this function minus this function, which is actually the same function. And this is very weird. So actually, you should not even think of it in this way at all. This is what I mean by do the whole thing sideways. So instead of these rectangles, we do rectangles like that. These are sideways rectangles. And these rectangles, they always do go from this function to this other function. There's no rectangle which has both ends on the same function. That's why you have to do it this way, sideways. We still have a bigger function and a smaller function, although they are bigger in terms of x values. This one is the bigger one because its x values are greater. They're further to the right. And this one is the smaller one because its x values are lesser. So the moral of the story here is we set up everything sideways, which is to say as x equals some function of y. We're going to do everything in this kind of sideways way. Even if one of your functions was given to you as a normal looking function, you have to change it around so that it's a function of x in terms of y. But then you can still do the integral as the bigger minus the smaller, where the bigger is, in this case, bigger means further to the right, because I'm talking about bigger x values, and the smaller means further to the right. Further to the left is the smaller. Okay, so anyway, in this case, my function over here is y equals 1/2 x, and my function over here is x equals y squared minus 3. So set up everything as x equals f of y. Well, one of them already has that format, so this is fine, as is. But the other one we have to move around a little bit, and it's not difficult. All you got to do really is multiply both sides by 2, and you will have solved for x. Question, yeah?
But you originally graphed them in the same as y equals 1/2 x. You don't change it then graph it.
You could change it and then graph it if you want to. Yeah, it's the same. Yeah, I mean, so the way, in this case, the way to change it is to multiply both sides by 2, and you get x equals 2y. This and this are the same. So when you graph them, it looks the same. Yeah.
Would it have been beneficial earlier on to change the x equals y squared minus 3 to like y equals red x minus 3 or something like that?
This is not a terrible idea, just because in general, I don't want to do it sideways. It seems like that's, like I usually don't like to do everything in terms of y, but if you change it to square roots, then you end up missing half of the graph. Like the square root is only the positive side. So if you actually did that, then it actually messes up the picture. You lose the bottom half of this shape. So you really do have to do it in this way. Unless you also introduce a plus or minus, but you don't want to do an integral which has a plus or minus inside of it. That you have to think a lot harder about things. All right, so this one I have solved for x here. And now we integrate, as usual, sort of big minus small, where big in this case means further to the right and small means further to the left. And then we should talk about the endpoints that I'm integrating across from. Now, usually we go from x equals a up to x equals b, but I'm doing everything sideways in terms of y. That means really the endpoints that I'm talking about here would be the y values at the bottom and at the top, because everything is being done sort of in this direction. I'm going to write my integral as a dy. And the dy starts at that point at the bottom, and it goes all the way up to that point at the top. All right? From y equals whatever to whatever. And we have to figure out those points. But this, again, is just by setting the formulas equal to one another. This is how you find the intersections of two curves. So here we have these two curves. I can set them both equal to each other easily because they're both solved for x here. So to find the intersections, I set those guys equal. I just get y squared minus 3 equals 2y, right? And now I'm going to solve this for y. This is a quadratic, so I should get two values of y. And those will be the two boundary values, the bottom one and the top one. So to solve this, it's a quadratic, so I'm going to put everything on the same side and then factor. Y squared minus 2y minus 3 equals 0. Any factoring masters out there? What do you say?
1 and negative y minus 1 and y plus 3.
I think he said y minus 3 and y plus 1. I agree. Yeah, it should be minus 3 and plus 1 to get the minus 2 in the middle.
Oh, gotcha.
Great. Mostly. All right, and then, so to solve for y, I get y equals 3. Maybe this is what you meant. The actual answers are y
Yeah,
equals
that's
3
right.
and y equals minus 1. Yeah, great. All right, I think we're totally ready now to set up the integral. Once you set it up, this, again, is an easy integral to actually do. But it's going to be the integral from y equals negative 1 to 3, because those are the boundary values that I just found. And then each time, or the function I'm integrating is the bigger minus the smaller. By bigger and smaller, I mean further to the right versus further to the left. So the big function is this one, which is 2y. So here I go 2y minus the other function. Sorry, it's scrolled off there. Y squared minus 3, like that. dy. And this is sort of fully set up now. Maybe I'll distribute the minus sign before going crazy on it. Like so, all right? These area between curve problems tend to have sort of long and somewhat difficult setup. If there's any hard part, it's probably in the setup. Doing the actual integral is usually just kind of a formality at the end. This is how it goes. Anyway, let's do the integral. So this 2y becomes y squared, minus y squared becomes minus 1/3 y cubed, plus 3 becomes plus 3y. And I plug in minus 1 and 3. And then we just plug everything in. So it's 3 squared minus 1/3 3 cubed plus 3 times 3 minus, plug in negative 1. Negative 1 squared minus 1/3 negative 1 cubed plus 3 times negative 1. There you go. This is my final answer. As usual, if you want, you can plug that into your calculator, but I don't want. All right, any thoughts about that one? I got a couple for you to try, one of each, kind of each type of these. And then we can, time permitting, we'll go on to something else also. And I'm gonna walk around and make sure everybody's doing well. Okay, so the first one here is find the shaded area. This is one of those ones where you have to first find some intersecting points. Okay, I have one line. This is y equals 3 minus x, and then I have a parabola. Sorry, that's lopsided parabola here. That's as good as it's going to get here. This is 3x minus x squared, and I want this area here and here. All right? So this is one of those ones where you have to break it into two pieces. You'll have to figure out where that point in the middle is to tell when to sort of transition from one piece to the other. All right? And then I got another one. This is a sideways one. All right, see what you think. Of course, you can't fit the answers all in between those two that I drew. I just want to get them both on the screen at the same time. As usual, I'm going to walk around. Please let me know if you have questions. I'm not going to collect these or anything, but you will see homework problems similar to these on the homework. So put it all on one side. Okay. Yes. These two numbers here, you have to measure okay here? Yeah, it was good. Getting rid of the factors.
So 0, 1, and 3. Yeah.
That's right. First one, okay? Yes. So we should.
How close you are.
We should be like a bar on the right side. Not a bar.
Yeah, that's good. Maybe I did our one.
Doing okay? You got the first one?
Yeah.
Alright. All right here? You're gonna want that. How's it going? Yeah. 0, 4, 0, 1. You should do that. So he says 3, 1.
Or I guess the other way around, it's just one.
This
This side is over 3. Over here, 0.
How's it going?
This one, I would suggest like with the other first to explain maybe switch the signs with it. I don't like when there's signs in I'm not sure where you're gonna go from here. Yeah, I mean, you do have to say something to cement self, correct? So you want,
What's your answer?
you wanna factor that into the stuff.
He just said just plug it in.
No parentheses, no parentheses.
Maybe it did something.
And that
Too much.
to
But
get it
like right, you're just plugging in the one
means easiest to
into the
do
whole
it
thing.
with the expert.
and then you subtract it from the 0, so I just expanded to get there. I didn't actually solve anything.
Yeah, but it's negative.
This one. I think that's right.
Yeah, so
Like,
it's a negative versus plus. Yeah, that's right. But then you can, like, this is 0, so you can just say multiply both sides by a negative. Swap all the signs. Like, yeah.
Or just like,
Oh wait, is it plus? Plus, right?
yeah, the 2 with plus is
Right, right, right.
That
Yeah,
was
just distribute it to them.
Right side?
Just make it
Okay.
It's
still right.
I just write it like as I do it, I just put
The second
plus the
one.
whole time.
How do you get it? That's just
Still doing okay here? Still doing alright? Still good here? It's like cleaning up your room. You alright?
Yeah.
Good.
Yeah. I decided I overdid it this one.
Alright, great. Doing okay? Still good here?
Wait, are you saying that point of 1?
Okay. Yeah, I'm just gonna try.
Yeah, this is the y value.
Okay, alright.
And down here is, 0.
Alright.
Yeah.
That one's a little easier because you don't have to find an intersection.
Perfect.
You can just go the y value goes from 0. What about the first one, okay?
Yeah, I should expand it, but I think so.
Doing good? I like it better when you can see the part because I don't know if it's Yeah, great. Still doing okay? Looks pretty good. Sorry. Still good here?
Yeah, put it like this.
Great. Yep. Still doing all right? Still good? Just a little this. I would rather you like put the numbers in so that I know what number to put in.
And then after that,
Yeah. Still good here? Great.
I'm just confused. So there's a loop in the intersection for that one. That's right. So assuming that once us get to that first step, before plugging in, what these terms are with meters or lines.
Well, it's actually a little bit easier because there are no
I like-
intersections.
I saw it
So
in
the integral
of course,
is just
here
goes
is
from
I don't know how to look at
it's one of those sides which you so it goes
Yeah.
from the bottom up to
Yeah.
the top.
Okay, I see.
What are you supposed to do for it? Do you know?
Still good here? Yeah, it looks pretty good. Great.
So change the integral for y.
Like you can do it either way.
Yes.
Three solving
That's right.
for this one. Like the
You can
in terms of
actually know your number.
yeah, yeah. Let me.
Oh, so 5, 6.
So I like this line. This is good.
5, 6, 5.
Yeah,
Yeah, 5, 6.
yeah.
And the final answer for the
It just looks- Wait, where does it why?
Yeah, so now I'm not doing
Why should be y? Oh, I see what you're saying. I'm saying dy. If you do dy, that's
this.
So I got here.
Set them all equal.
Right,
set them all
Yeah.
equal.
Yeah, that's,
Okay.
Is there anything that happened here?
Yeah, because you need values here.
yes, that actually is.
Oh,
That tells you the range of the y values in this case.
Oh, and then
They did it.
Sounds like nice.
So you want just that shaded region there?
yeah.
So you just think about what's
0 to
the
1.
y, yeah, the y of the problem is 0 to 1.
Okay. Okay.
All right, can we go over these? I see various people at different different stages. Some people totally done. Some people still finishing off the first one. That's all right. In general, I don't really care if you can do these kinds of problems fast. I care that you can do them eventually. So let's look at the first one first. A lot of people had a little roadblock just finding this intersection point, but it should be done by setting the two functions equal to one another. So I go 3 minus x equals 3x minus x squared. Now for me, I find this easiest if I just put everything on the left side. So I'm going to add x squared to the left side and also subtract 3x over to the left side. It'll say x squared plus 3 minus x plus 3x, minus 3x, sorry. It's a somewhat weird order that I wrote it in, but just to simplify a little, I want to make this look like a sort of an ordinary quadratic. X squared minus 4x plus 3 equals 0. All right? And then I can factor this. Hopefully you remember how to do this kind of simple factoring. It's x minus 3 and x minus 1 in this case. So x equals 1 and x equals 3 are where these intersection points happen. So x equals 1 apparently must be there, and x equals 3 I guess must be right there, because those are the intersections. Any questions about that so far? This is easy to make a little mistake in here and then you can't factor it and then you're like totally stuck, but I hope that didn't get you stuck for very long. Anyway, now I do each of these separate regions by doing the appropriate integrals of the bigger minus the smaller. Yeah?
Do we always assume that it's bounded by the y-axis?
No, but just because I said the shaded area and that's where I drew it in.
Okay.
I mean, in this picture it is bounded by the y-axis, but it's not always going to be. Yeah. Okay, so can I just say like the sort of the left region would be integral from 0 to that first intersection point, which is 1. So that's this range of x values from 0 to 1. And then the bigger minus the smaller would be the line 3 minus x minus the parabola part. So this is 3 minus x minus whatever the other part was, 3x squared minus, no, 3x minus x squared. Right? This is the integral for the region on the left. And just to simplify and do the integral, this becomes, add this all up, it's x squared minus 4x plus 3 dx. And then I go 1/3 x cubed minus 2x squared plus 3x. Plugging in 0 and 1 gives me 1/3 1 cubed minus 2 times 1 squared plus 3 minus a whole bunch of zeros. All right, so this is my answer for the region on the left. And it seemed to me most people got something like that. I saw some people with some kind of primal urge to simplify until they got a final answer of just a number. That's all right. If you, I don't want to yuck your yum, as they say. Any questions about that? That's the left-hand region. And then the right-hand region is very similar. It's just the other way around in terms of the function that you're doing the integral of. So I will dump this down a little farther. The right region would be this time the integral from 1 to 3. That's the range of the second part. And then what I'm integrating this time is those two functions, but subtracted the other way around. So it's like this. So this, when you sort of resimplify everything, becomes negative x squared plus 4x minus 3 dx. And then I do the integral. Minus a third x cubed plus 2x squared minus 3x. Plugging in 1 and 3. I hope I'm doing this right. Plug them in. So it's minus a third times 3 cubed plus 2 times 3 squared minus 3 times 3 minus a third times 1 cubed plus 2 times 1 squared minus 3. And this is my final answer for the other part. And of course, the overall total answer is the sum of those two halves. Everybody knows that. Any questions about that one? It's a little long-winded. I hope it's not too much trouble, though. All right, great. Let's try the other one. This one is one of those sideways ones. This one may be a little easier than the first one. I don't know. Once you realize what you're doing, there's not as much to it, in my opinion. So this one, first of all, you do have to solve each formula for in terms of x. So we have x equals y squared. That one is already. But the other one, I also want to solve for x in terms of y. It would say x equals y minus 1. All right? Now, in some situations, you would need to find the intersection points between these two graphs, but in this case, we don't, because you can see on the picture, I'm not talking about, actually, these two graphs never intersect one another, but anyway, I'm not talking about a region that's bounded by intersections. It's just this region, which I told you to go from here to here. So these are my two functions, and I set up the integral as the bigger one minus the smaller one from a certain range of y values. What did you use for the range of y values? It is 0 to 1. Yeah, I'm going in terms of y here, and this is the region I'm talking about. So you have to start with y equals 0 at the bottom up to y equals 1 at the top. So I go integral 0 to 1, and then I'm going to do bigger function minus the smaller. Since it's in terms of x, that means larger x value, which is the one to the right, minus the one to the left. So that would say y squared minus the other one, y minus 1, like so. Right? And now we do the integral. Don't forget those parentheses, haters. My haters is my motivators. I think, who said that? Did somebody say that? Is that something that people say? Or did, no, all right. I think I heard Ellen say that once. Ellen DeGeneres? I don't know. That was before she had real haters. Now she's got real haters. Right? This is the integral. Sometimes I do integrals while talking about Ellen. Yeah. Plug in the 1 and the 0. I get 1/3 times 1 cubed minus 1/2 times 1 squared minus 1 minus, and then plugging in zeros everywhere is going to give me 0. I must have messed something up.
Yeah, it's minus y.
I messed up the sign on the 1 there. Yes. So plus 1 at the end makes a plus y, makes a plus 1 back.
Do we have to write
Something else?
0, or can we just like them?
No, I mean, if you can do that in your head if you want. Yeah. All right. Excellent. That's all I had to say about areas between curves. All right. So class is not over though. We got another 20 minutes. The homework assignment is going to cover up through this material. So we're going to do some more today, which will not be on the homework this week, but it'll be on it next week. Yeah.
Is there ever going to be problems where there's more than one extra intersection point? Like that's something I did in high school.
Yeah, I mean, it's possible
Okay.
if I wanted to be a hater like that. But yeah, I mean, yeah, it is possible. I would say, I don't recall actually if there are any on the homework like that. I probably wouldn't make you do one like that on a test. just because it takes, I would say it's not really harder, it's just going to take you 50% longer to do. So, yeah. Any other questions about that? Great. Let's move on to the next thing. The next thing on our big list of topics is using the area to find volumes. In particular, this is what they call volumes of revolution, which I've always thought is sort of a silly name, but I suppose it kind of makes sense. Volumes of revolution. That is, you can use the integral to find volumes of certain shapes, even shapes that you don't really know offhand a formula for the volume of. This works best if they are shapes, what they call of revolution. That is a shape which is obtained by revolving a function, kind of like a thing that you could make on like a pottery wheel or something. A shape which has some kind of rotational symmetry to it. I'm referring to something like, I'm going to go beyond the bar here. Something like if I have a function here that maybe looks like that, this is just a little piece of a function. Of course, you can find the area under the curve by doing the integral, but you can also use the integral, it's not so hard, to find the volume of revolution. That means it's the volume that you would get if you took that same shape and spin it around the x-axis like this, and you get, in this example, some kind of a, I don't know, a pot, an Erlenmeyer flask. Is that what that looks like? Something like that. I am talking about a round thing, which you would obtain if you spun that line around the x-axis. All right. This is referred to as a volume of revolution, and we can find volumes like this using the integral. And it's not so hard to do if you know how to set it up. We can find volumes like this with an integral. This is kind of a very, you might say, weird and specific type of shape. Like ordinary shapes in real life do not necessarily look like that, like, you know, this box here. Actually, it's fairly easy to find the volume of a box like this, but a box is not a kind of revolved shape in that way. But there are some ordinary shapes that you can obtain this way. Certainly, like a sphere is a shape which can be obtained by spinning something around. Or, I don't know, those water bottles there seem to be, they have the appropriate symmetry. You could find their volumes in this way. I would just fill it up with water and then measure the volume of the water. But anyway, we are going to use the same old idea that we use for all of our applications of the integral, and that is, I'm going to try and draw this shape again. The same old idea that you always use for the integral is we cut it up into bitty bits and then add them together. And I will just say, sort of parenthetically, this makes an integral. Like, this is where integrals come from, by chopping a shape up into a bunch of tiny bits, imagining those bits are like infinitely tiny, and then adding them all up together. So this makes an integral. Now, in a traditional integral, you are chopping a shape up into rectangular areas. That's not true in this case. I imagine that I have a volume, and when I cut it up into sort of like super thin little slices, can anybody say what does each of those slices look like? It doesn't look like a rectangle. In the traditional integral, when you slice it up, they look like rectangles. What does it look like here?
Circle.
Yeah, it looks like a circle. Like if you were to sort of grab one of these things and pull it out, I would say it looks like a disc. It's a circle, but it has some thickness to it, right? So in this case, when we cut it up, each bit here is a disc. It looks sort of like this, and then it has some kind of thickness to it. That's not a great picture. I'm talking about something like this, where this thickness here is like what we usually call delta x. That's the width of each of the slices. we typically call delta x, all right? And we would like to add up all the volumes of these little bitty disks, right? There are a bunch of little disks, and we want to add up all the volumes of these disks, all right? Anybody happen to know the formula for the volume of a disk type shape like that? Actually, this, I'm calling it a disk, but there's another name for that shape which you probably do know the volume of.
Is it pi r squared times height?
Pi r squared times the height. Yeah, this is actually a cylinder. It's kind of like a very short cylinder that's turned on its side, right? And probably, I don't know if you still remember it, but at some point in your life, I'm sure you knew there's a formula for the volume of a cylinder. And he said pi r squared times the height, where certainly what he means by r must be that distance right there. So I'm thinking of that as the radius of that cylinder. And the height is actually what's labeled delta x on my picture, right? Usually you draw a cylinder standing up the other way, and that becomes the height. So this volume is pi r squared times the height, which is delta x, all right? And can we say anything about r? Like, what is r in terms of my original picture here? The idea is I started with this thing, which is obtained by starting with a function. So it's like this line on top is given by some formula, which is a function. And what can you say about the r?
Like f of x minus the x-axis.
Yeah. Yeah, the r is sort of, if the x-axis goes here, the r is just equal to this height, wherever it is along the x-axis. And what is that height? Actually, that height equals f of x. That's like the whole point of what f of x means. Y equals f of x. It tells you the y values along each thing. He said you subtract f of x minus the x-axis. I mean, that's like f of x minus 0 all the time. So this r, actually, this is not going to be a very complicated formula here. Here, according to the whole setup, r just straight up equals f of x. That's it. It's just equal to the height of that curve as you move across the picture. All right? So, in conclusion, so each disk has volume pi times f of x squared times delta x, all right? The radius, this f of x squared comes from r squared, the radius squared. All right, and what do we get when we add up all of the volumes and simultaneously take the limit as delta x goes to 0? So we sum these, and we do the lim as delta x goes to 0. This creates a Riemann sum, which is equal to this integral, the integral pi f of x squared dx. Because what you get if you take a sum and you make the delta x go to 0 in the limit, what you get is a Riemann sum which equals an integral. All right? Now we should talk about the boundary values. I haven't been very specific about this yet, but basically you go from over here to over here, and if these endpoints are like x equals a and b as we usually call them, then this integral is the integral a to b. All right?
Can you take out the pi?
Yes, the pi being a constant inside the integral, you can always factor a constant out of an integral. And so if you like, you can write this formula with the pi on the outside. And I think that's, I was going to write this again and put it in a box. I think I'm going to put it on the outside. So when, this is my little sort of conclusion here, when the graph of f of x is revolved around the x-axis, the volume from x equals a to x equals b is, and you can put this in a box in your notes somewhere, pi integral a to b f of x squared dx. This is a formula to remember. This is sometimes called the volume of revolution formula, something like that. Basically, this formula just comes from pi r squared, but I don't really suggest you try to remember the whole derivation of it. It's probably easiest if you just remember this formula. Yeah?
Where does delta x go? Or is that like the height?
The delta x, the height actually is f of x. The delta x is the width of each of the tiny little bits.
Okay.
And when you convert a Riemann sum into an integral by taking the limit as delta x goes to 0, the delta x kind of disappears and becomes the dx.
Oh, okay.
Yeah, I'm not sure if I want to get into more than that. At a theoretical level, it always happens when you have a Riemann sum where you have your tiny width parameter, that always turns into the dx, and then everything else turns into the rest of the function. Yeah.
Can you scroll back down?
Yeah, sorry. That's the one you want in the box. All right, let's try one example. I think we've got time for one example, and then we can do some more next time. All right, how about, this is maybe like the simplest example you could think of. Not quite the simplest, but I would like to know, tell your friends, how about just this parabola, y equals x squared, and I want to revolve this. Oh, that's terrible. That's all right. And go up, from 0 out to x equals 1. You get this kind of horn shape, sort of a bugle, if you will. I want the volume of that kind of horn shape. Volume of the bugle. Remember bugles? Do they still make those?
Yeah.
Those are good, yeah. Just tastes like salt, nothing else. It's like the most pure snack food. All right. Get some bugles this weekend if you never have. You're in college now, right? You can have bugles whenever you want.
Is there any chance I missed one thing if you scroll for a second?
Sorry, I'm talking about bugles here. Even more?
Yeah, it was like a couple minutes ago I missed it.
All right.
I think it's a little bit more up. Right there.
But their like shape doesn't work like that.
All right. Can we do the bugle thing? We should set up the integral from the box. I'm trying to say this while he's frantically copying down what's on the screen right now. It should say v equals. So I'm using the formula in the box. All we need to do really is say what are the a and the b and what's the f of x. Can anybody say what are the a and the b here?
0.
They are 0 and 1, just on the picture. And then what's the f of x? It's this function, x squared. Now there's a squared, and there's also a squared in this formula. This is not really all that difficult. But anyway, we set it up. V equals pi integral a to b, f of x squared dx. A and b are 0 and 1, like they all said. F of x is my function x squared. So it's actually x squared squared dx. So this is pi integral 0 to 1, x to the 4 dx. And this is an easy enough integral to do, right? You just do it. So it's pi 1/5 x to the 5, plugging in 0 and 1. Plug in the 1, I get pi times 1/5 times 1 to the 5. Minus, plug in 0, you get 0. So my answer, apparently, is pi over 5. That's the volume of that bugle, if you will. All right. We got 5 more minutes, but I think maybe this will do it for now. So check out the assignment, the homework assignment. I will send out to everybody the book pages this time. Hopefully by next week we will have the book all settled. Please let me know if you got questions about anything. Have a good weekend.